In this video, we are going to analyze the time response of this general first order system to a unit step input. We know that the ratio of the output to the input is just our transfer function g of s, and it is just 1 over tau s plus 1. So our y of s is just u of s times 1 over tau s plus 1. So for a unit step input, u of s is just 1 over s. So we have y of s to be 1 over s times 1 over tau s plus 1. So in order to know the steady state value of my output, I can use the final value theorem, which says yss is just limit as s approaches 0 of s y of s. So I will have yss to be limit as s approaches 0 of s. Then I have my y of s, which is this lot here, so which is 1 over s. Then I have times 1 over tau s plus 1. So s will just cancel s, and substituting the limit, my yss will just be 1 over tau into 0 plus 1. So I know that my steady state value is just 1. So since I want to analyze the time response, I have to convert my y of s, which is in s domain, into time domain. So you can see it is in form of 1 over s all over 1 over tau s plus 1. So I can't find the inverse Laplace transform directly from this relationship. I need to use partial fraction decomposition in order to have it in parts that I can actually find the inverse Laplace transform. So for 1 over s into tau s plus 1, I can decompose it into a over s plus b all over tau s plus 1. So I will have 1 over s into tau s plus 1 is just s into tau s plus 1. So s into tau s plus 1, I will just have a into tau s plus 1, and then I will have plus bs. So now I can multiply both sides by s over tau s plus 1, and I will have 1 is just a into tau s plus 1 plus bs. So I can open up the bracket. I will have a tau s plus a plus bs. So collecting like terms, I will have s into a tau plus b, then plus a. So comparing the left hand side and the right hand side, I can see I have my constants as just a is equal to 1. So I don't have coefficient of s in the left hand side, so it means a tau plus b is just 0. So substituting the value of a into this equation, I will have tau into 1 plus b is equal to 0. So it means my b is just minus tau. So if I substitute the value of a and b into this relationship, which is just y, I will just have y of s is just 1 over s minus tau all over tau s plus 1. So it is just 1 over s minus tau all over tau into s plus 1 over tau. So tau will cancel tau, and I will have 1 over s minus 1 over s plus 1 over tau. So I know that the inverse Laplace transform of 1 over s is just 1, and that of 1 over s plus a is just exponential of minus 80. So taking the inverse Laplace transfer of y of s here, I will just have y of t. For this part, I will have 1, and for this part, my a is just 1 over tau, so I will have exponential of minus t over tau. So in time domain, the steady state value can be computed by using limit as t approaches infinity of y of t. So it will just be, substituting the limit, I will have 1 minus exponential of minus infinity, and that is 1 minus 0. So I will have 1, which is similar to the steady state value I obtained using the S-domain relationship. Also, for a general first order system, we know that tau is the time constant. So if we want to know the value of our time constant or the definition of the time constant, we just use t is just equal to tau. So substituting it here, I will have y of tau is just 1 minus exponential of minus tau over tau, which is 1 minus exponential of minus 1, which is 1 minus 0.368, which is just 0.632. So at the time constant, the amplitude is 0.632, and you can see the final value is 1. So that is why time constant is defined as the time taken to reach 63.2% of the final value. So let us jump to MATLAB and see the response of the general first order system in both S-domain and time domain. So this is the definition of the system in S-domain, and I use my tau to be equal to 1. And you can see this is the equivalent of the system in time domain as we have already found. So I use subplot to have like the step response of the system, and this is the equivalent using our relationship in time domain. That is for the second plot. So if I just click on run, so you can see that the response is similar. That is the transfer function in S domain and my output in time domain. If I want to have a faster response, I can just reduce my tau. So if I make it, for example, 0.3 and then click on run again, so you can see that the system responds faster now. So it is the same response, it's just that the scale, the time scale for the upper and the lower plots are different. Watch the video on the screen for time response analysis of a second order on the damped system to a unit step input. Please like and subscribe to the channel. Thank you for watching.